Welcome back, everyone. In this lecture, we're going to be talking about the self-inductance that happens in a circuit. Essentially, you run a current through a circuit that is sort of powered by an EMF source, and the change in flux that it's creating in and of itself, right, even if it's just a loop of wire, can create some self-inductance. So we're going to talk about that. We're also going to talk a little bit about inductors and what they do in a circuit. Okay, so let's get started. First of all, self-inductance. So the loop that we've set up over here on the left side of the page is a simple circuit with an EMF source. It has a resistor in it, and then right there just showing you a loop of wire. The circuit in and of itself could literally just be a rectangular loop, and it would produce the exact same thing. But just for the visualization, we took a bit of the wire and we wrapped it around in this loops on the left side. And you can see that the current that's being produced by the actual EMF source is coming through here, then it's traveling around the circle in a clockwise direction. To determine the magnetic field that's produced by that current, by that moving charge, we can use the right-hand rule. So you'd put your thumb in the direction of the current, and you can see as you curl your fingers around, the magnetic field is sort of looping into the page as you go around in the clockwise direction. So you have all of these fields that are kind of going into the page here, and apologies for the bell. When we are essentially just closing the circuit, the flux is going to change, right? When the switch is open over here, there is no flux through that loop of wire, and when you do close the switch, there is going to be flux, right? So you go from no flux to some flux. That is a change in flux, and when you have a change in flux through a loop of wire, you do get an induced EMF as well. And that's what we're calling this self-induction, or this self-inductance, where just by turning on or off the circuit, you're going to induce an EMF that's opposing the change in flux. So, what's happening here? Well, as soon as you close the switch, you are inducing you're not inducing, but there is an EMF that starts to build up from 0 up to the full amount of let's say 12 volts. As you go into this loop, we can see this magnetic field is being created, so there's a flux that's changing from 0 to something, and because there's more field lines that are now going into the page, the induced EMF is going to create field lines that are coming out of the page. So they're basically in the exact opposite direction coming here out of this page. So I'm going to call this we'll just say self-induced, right? It's the self-induced EMF. Okay, so what direction is the EMF? Well, if the field lines are coming out of the page, that means the self-induced EMF that caused those field lines would be in the opposite direction. So you actually have a current running, right, and again we'll call this the self-induced current, opposing the current in the wire already. Okay, so what does this actually do? Well, it's this induced EMF, or this induced current, is opposing the battery, but it's not equal to the battery, right? It's actually going to be less. So what happens is, there's a big change in flux as soon as you close the switch, and what this self-induced EMF does is kind of slows that current down a little bit, right? It's going to, instead of immediately just going to the maximum amount of current, it's going to slowly build up to that current because of this opposing EMF. That opposing EMF is going to kind of wane over time to the point that the current just gets up to its max amount. And when it's at the full current over some period of time, the circuit is in steady state and there's no longer any induced EMF, right? Because the flux wouldn't be changing at that point, right? It's just some constant magnetic field. Okay, so what are inductors? Like, how is this useful? Why would we want something that's actually opposing the current? Well, we put inductors into circuits for various reasons, but one reason we would do it is because it will it would help preventing like a big surge in current. You know, when you're building circuits, you don't want the parts of that circuit to be damaged in any way. If you get a high surge of current or a big spike at any point, it could cause damage to the components, right? It could cause overheating, it could cause fires, could cause all sorts of things. So by putting an inductor into the circuit, you're essentially adding a buffer there, right? If you get a big surge, it's going to slowly allow it to get, to build up to that. It's not going to just instantly jump there, and essentially give, the components of the circuit time to react if they need to, right? If the fuse needs to blow, or if the circuit needs to switch off, or something like that, it's going to give it that little bit of time that it needs to execute something that will, break the circuit so that it doesn't actually get to a dangerous level. Okay, so that's what inductors are. They essentially look like tiny little solenoids, right? Just loops of wire, because a loop of wire creates this magnetic field. So by putting these additional loops of wire into a circuit, you can actually, again, make it safer. So there's two ideas here, right? One is the idea that, okay, you can actually put a specific inductor into a circuit that will create an opposing EMF when there's a big change in flux. There's also just the idea that if you have a loop of wire, it's going to self-induce an opposing EMF, right? It doesn't actually have to have an inductor in the circuit to do so. All right, just so we know, the inductor symbol kind of looks like that. And L is going to represent the inductance, right, which is sort of a measurement. It's kind of like resistance, but it's a measurement of the inductance, or how much induction is going to occur when you change the current going through a wire. So we'll get back to that in a moment. But let's start thinking about some relationships here. So we know the induced EMF in a circuit is equal to the negative change in flux with respect to time. Thinking about how this self-inductance works, apologize for the bell again, thinking about how the self-inductance works, it has to do with the amount of current, right? So if I think about it, the more current I have, the more the more magnetic flux is going to be in this loop, right? There's going to be more magnetic field, so ultimately more magnetic flux. So our magnetic flux is proportional to the current, right? Now, these aren't equal because there's some constant that must associate these. So if I say that, okay, if I increase the flux, I'm going to increase the current, there's a direct relationship here. There must be some constant of proportionality. We're going to call that L multiplied by I. So the flux will equal some constant of proportionality multiplied by the current. And that constant of proportionality is what we call the inductance. Right? Again, very similar to the EMF that we've created, thinking about Ohm's law, the EMF related to the current, right? If I increase the EMF, I increase the current. There's some constant of proportionality there called the resistance. Well, this is the same thing for magnetism here. The magnetic flux is proportional to the current, so there's some constant proportionality, which we're going to call inductance, L. And inductance is really based upon the physical dimensions of the actual loop itself, right? If I have multiple loops, it's going to increase the inductance. The shape of the loop, the area of the loop, that kind of thing is going to affect the inductance, right? Just like the physical dimensions of a resistor affected the resistor. Okay, so let's pause that idea there. Let's jump over to the next page. Here's just two examples of, again, what's happening. So this is as if I put an inductor into the circuit. Again, there is self-inductance, which happens whether there's a inductor or not. But then there's also, if you can put a physical inductor in there, or you could at least model the self-inductance with an inductor, right? If you were just modeling it in a circuit. And again, it really would go for all circuits because all circuits are loops. So, in this first scenario, you have the current that's traveling to the right, and it's going into an inductor. If the current is increasing, an EMF is going to be induced in the inductor that opposes that increase. Again, it's not equal, but it at least slows down the increase in current, right? It's called an impeding. It's impeding the change in current, right? So it's slowing it down a little bit. So now you can see you could basically treat this inductor as an EMF source in the opposite direction if the current is increasing, right? That's why they're showing you this symbol for an EMF source that's opposing. Now, in the second situation, you have the induced EMF that opposes the decrease. So instead of increasing the current, we're decreasing the current. So it's still to the right, right? It's current still to the right. You're still going through an inductor, but you're decreasing the current. So the inductor is going to create an EMF that opposes that decrease, which means you're going to have more EMF to the right, which is the direction of the current anyway, so you can almost treat this inductor as an EMF source to the right. So, something to think about is, well, what if the current wasn't changing? What does the inductor do, or what does it act like? So if I were to draw that situation down here, where let's say there is no change in current. Well, if there's no change in current, there's no induced EMF. But the inductor is still a coiled wire, so there's still current going through the coil. It's still creating a magnetic field, but none of those fields are changing. So there's no induced EMF. So essentially, the inductor just acts like a wire instead of like a battery. Like an EMF source, right? So you can really just replace that if you're at steady state, which means it's sufficiently passed when you've closed the circuit. If you're at steady state, you can just remove the inductor and replace it with just a wire. Okay, so we're going to pause here, actually before we pause, let me go ahead and just give us the equation for the induced EMF due to an inductor or to self-inductance. And it's coming from that expression we had on the previous page. So if the magnetic flux is equal to some proportionality constant multiplied by I can take the derivative of both sides here and kind of relate them to the change relate them to the induced EMF, right? So really what that means is the induced EMF is going to be equal to minus times the inductance times the rate of change of the current with time, right? Because again, the derivative of the left side of this, multiplied by a negative sign, is the induced EMF, right? We know that from our induced EMF equation. I'll just put that again up here to remind everyone that the induced EMF is equal to the negative derivative of the flux. So again, if I take the derivative of both sides here, the induced EMF, and relate these two equations together, the induced EMF is minus the inductance multiplied by the rate of change of current. So just to point this out, because these symbols are very similar to each other, this is current rather, not flux, right? This is the rate of change of current. Okay. All right, so that's all we have for this lecture. In next lecture, we're going to be talking about RL circuits.